we're going to introduce a new term. It doesn't have a really big meaning that's different. Okay. So our topic today, enthalpy, or enthalpy, depends on who you talk to. Enthalpy is related to heat. Okay? And because it's related to heat, they gave enthalpy the abbreviation H. They should have picked something else, but they couldn't use E because if it's related to heat, it's also related to energy. And E usually stands for energy, so they couldn't pick E. They picked H. And what it is it's the heat content at a given pressure. How much heat that thing has. How much heat energy is in that chunk. Because you know when you pull the pizza out of the oven, it's got some energy. How much energy does it have? Okay. And the reason why it's tied to heat is because the way we find that energy is by seeing how much heat it gives off. Okay. Now you can't measure H directly because then you have to define what is zero heat content. And you have to compare it to zero heat content, which we can't get to. It's much like an odometer, the thing that keeps track of miles on a car, where you didn't start at zero, but you don't know where it started. Okay? So you buy a car, it's got some miles on it, but they say, I bought the speedometer 3 years ago, the odometer 3 years ago, I put it in, so those aren't the real miles on the car. Yeah, you got to sign all that on the back of when you go to sell a car. You got to talk about whether the odometer's messed up, all those pieces, okay? But does that mean I can't figure out how far I drove that day? No, I just know where I started and where I ended, and I can subtract, right? Well, the same thing is true of enthalpy. We can't give it a number. We know exactly how many miles we've driven. We can't say exactly what the heat content is, but we can measure how much it changes by seeing how much heat it gives off. If you got this much heat content when you start and you have this much heat content later, the difference between those two is how much heat you got rid of. So if you measure the heat that comes out, you can measure how much the heat content's changed. So what we measure is not H, but delta H, how much the heat content's changed. So we're going to use delta H in place of H lots of times. So that leads us to something called calorimetry. Okay, so people taking Spanish should recognize that. People taking French should recognize that. Calor. What's calor mean in Spanish? Heat. Okay. In French, heat. Okay. So metrie means to measure, so it literally translates to measuring heat. So calorimetry is measuring heat. The device you use is called a calorimeter. So a calorimeter does calorimetry. Okay. And there's two kinds of calorimeters. And the one we're going to use is called a constant pressure calorimeter. Although most times, most people just call it a coffee cup calorimeter. Why a coffee cup calorimeter? Because these are important components. Styrofoam coffee cups. Okay. So what you do is you start off with a heat capacity for material that you know. Okay. So we got C for that material. And if we know how much material we have, then we can use Q equals MC delta T. We use Q equals MC delta T, and the material they use most often is water. Okay. So they fill a coffee cup full of water, and then that number 13 that we did on the bell work or the question today, that was a calorimetry experiment. They had 100 grams of water sitting in a dish. They heated up some metal. They took that 100 grams of water, put it in a foam cup, and saw how much the temperature changed. So this is what an experiment using calorimetry would look like. My magnesium good. Okay. So here I've got Q is the abbreviation for heat. I don't know why they picked Q. Okay. So here I'm going to take a 50 milliliter solution of acid. Okay. This solution is mostly water, so it's 50 milliliters of water. With a little bit of acid in it. Okay. And I need to take the temperature of it. So I'm going to take the temperature of it. So I put a temperature probe in. So everybody can see it. So I'll start up the program. Okay. Okay, so right now it says that solution is 21 degrees Celsius. Okay. And all I'm going to do is do a reaction. Okay. So I'm going to do the reaction you guys did in your oxygen generator. Right? I'm going to put in some zinc, or your hydrogen generator. Okay? And then record the temperature over time. Come on, react for me. Start reacting. The finer pieces. Come on. A little bit. So that temperature is going up. Okay? And we just watch it go up. Because look at what I know. I know that I've got a solution that's mostly water, 50 milliliters of it. I'm going to be able to see its temperature change, and I know the specific heat of water. Specific heat of water is 4.18. I'll be able to see the temperature change here. And then I know the mass is at 50 milliliters, and water is 1 gram for every milliliter. So I get about 50 grams. And as this reacts, the temperature will slowly go up, and we just wait for it to stop going up, which means the reaction has stopped. Stir it a little bit, get things moving. And so that's the kind of data you get. You measure how much stuff you put in the dish, you measure how much the water changed temperature, and you use the specific heat of water. So we'll come back to that one in a minute, but because it's still reacting. Okay, so this says the specific heat of graphite is, they give me a specific heat, so they've given me C. Calculate the energy, that's heat, or Q. Raise the temperature of 75 kilograms, that's a mass. From 294 to 348 Kelvin, that's a change in temperature of 54 Kelvin, which is 54 degrees Celsius. Because every degree Kelvin is a degree Celsius. Oops, sorry. What the heck just keeps going? So Q equals mc delta T. Heat equals mass times specific heat times change in temperature. And since Q is what I'm looking for, that means I need the mass, but I don't want the mass in kilograms.
It would be 7,500 grams.
So I get rid of kilograms, change it to grams. 1,000 grams is a kilogram, so 7,500 grams. Or 75,000 grams, sorry. Times C. Well, they told me it was graphite, 0.71 joules per gram degree Celsius, times the temperature change of 54 degrees Celsius. So 75,000 times 0.71 times 54 equals 2,876,000 grams, or 2,900,000 grams. No, not grams. It's not grams, is it?
It's joules.
Because the grams canceled. The degrees Celsius canceled. It's joules. Which is good because I was looking for a heat. So to call it calorimetry is not doing different math. The calorimetry is just a specific heat problem. You're just going to get your numbers from someplace else. Okay. Still going up. 24.6. 4.8. Still going up. 25. Okay. So, we don't have time for this to finish, but how would we do the problem? Okay. Well, I know I started at 21.4, right?
Wasn't it
21.8? 21.9, sorry. 21.9. I went to 25.2. So how much did the heat change? The temperature change. So 25.2 degrees Celsius minus 21.9 degrees Celsius is 3.3 degrees Celsius. That's how much the temperature changed. How much stuff did I put in my solution? I put in 50 milliliters, but for water, 1 milliliter is 1 gram. So it's 50 grams of water. And what I heated up was water. So it's 4.18 joules per gram degrees Celsius for C. So we can say this reaction, while we're watching here, that Q equals M, 50 grams, times C, 4.18 joules per gram degrees Celsius, times delta T, which we said was 3.3 degrees Celsius. So as the temperature is going up there, we've seen that this is released 50 times 4.18 times 3.3, 690 joules. And that's how chemists measure how much heat a reaction gives off. They let it happen in water and measure how much the water changes temperature. Make sense? Yeah. Okay. So, this describes a pretty common experiment. Well, we talked about the homework. Okay, so I got a 46.2 gram sample, and that's the mass of the copper. 94.5 degrees is the first temperature for the copper. 75 grams is the mass of the water. 19.6 is the first temperature of the water. And 21 degrees Celsius is the temperature 2 for both of them. So since I have a starting temperature for both and an ending temperature for both, I can find the change in temperature for both. The change in temperature for the copper was 95.4 minus 21.8. That's 73.6, I think. So the delta T for the copper is 73.6 degrees Celsius, and the change in temperature for the water is 21.8 minus 19.6 is 2.2 degrees Celsius. Notice that the metal changed temperature a lot more than the water did. Why? Because the metal's going to have a much lower specific heat than the water. Water has a really high specific heat. So the water doesn't change its temperature much. The metal changes its temperature a lot. So the question is, what is the specific heat of the metal? That's what the question is. So I want Q equals mc delta T. If I want to find C, I can divide by m and delta T. So I get C equals the Q over m and delta T. And I want the C for copper. So which of those numbers do I know? Do I know the heat the copper got? No. Do I know the mass of the copper? Yeah, I know the mass of the copper. The mass of the copper is 46.2. Okay. The change in temperature of the copper we said was 73.6 degrees Celsius. But if I want to finish this problem, I've got to figure out the heat for the copper. How much the heat for the copper changed. Well, they didn't give us that number, but they told us about water. And the water got hotter because the metal got colder, right? So the heat the water got came from the metal. So I can figure out the heat for the water. Q equals mc delta T. But if I stick in water's numbers, I know all those numbers. M, the mass of the water was 75 grams. C, water is 4.18 joules per gram degrees Celsius. Delta T, the water changed by 2.2 degrees Celsius. So I can figure out the heat for the water. And the heat for the water is going to equal the heat for the copper. Heat the water lost, the copper got. The reason why the water got hotter was because the copper got colder. What? Yeah. So 75 times 4.18 times 2.2. 690 joules. So that 690 joules goes right there. .203 joules, grams, and degrees Celsius. Joules per gram degrees Celsius, because nothing cancels out. Okay. So that's how they use water to figure out heats. But that heat came from a reaction. So we should be able to include the amount of heat in the reaction. Okay? So chemistry happens in moles. But we can actually put heat into the equation. And an equation that includes energy is called, not a chemical equation, a thermochemical equation. So if you put the heat in, you call it thermochemical. So up to this point, we up to this point, we have only dealt with chemical equations, but thermochemical equation just tells me, puts the heat in. Notice I put heat over here. So over here on the product side. The right-hand side is products. Products are the things we produce. So in this case, energy is a product. And if energy is a product, we have a word for things that make energy. And that would be exothermic. If I'd had to put the energy in, the energy would have been on the other side of the equation, right? It would have been with the reactants. So where the energy shows up in the equation tells you whether it's exo or endothermic. If it shows up in the products, that means you produced it. If it shows up in the reactants, that means you had to put it in. So if it shows up in the reactants, you put it in, that's endothermic. Products you get out, that's exothermic. But this actually, remember, this is a sentence. And a sentence we can read in moles. This says 1 mole of CH4 is going to make 802.2 kilojoules of energy. Because the coefficient 1 here and the number is 802.2. The coefficient in front of water is 2. So according to this equation, if I'm going to use this equation to make water, I'm going to make, if I make 2 moles of water, I'll make 802.2 kilojoules of heat. It's 2 moles of water.
But how do you get to the 2 moles?
Because it says right there, 2.
Oh.
So the coefficients are moles. So the 802.2 is when you use that many moles, or make that many moles. Oh, that means if I can write sentences like this, I can go from moles to joules, or from joules to moles. Because remember, our whole argument for going from moles to moles was 1 mole of CH4 makes 2 moles of water. Okay, because I can't make an equation with both of those pieces. I can't make not an equation, but a conversion factor with both pieces. Okay, does that make sense? So I'm just saying that you can interpret it based on reactants or products, whatever it is, that coefficient in front is how many moles of that stuff gets 802.2 kilojoules. If I use 2 moles of O2, I'll make 802.2 kilojoules if I'm doing this reaction. So here's our reaction. So if 10.3 grams of CH4 are burned completely, because this is complete combustion, how much heat will be produced? Whole last unit was if 10.3 grams of CH4 are burned completely, how much CO2 is produced? Now I want how much heat is produced. So since I got a balanced equation, I can do this with conversion factors. So I start off with the 10.3 grams of CH4. Now what unit do I want to get rid of? Grams, CH4. So where's that got to go? On the bottom. What can I turn grams of CH4 into? I gave a clue because I wrote 16.05. I turn that into moles of CH4. So this is just like we started the last one. Because this said grams, grams had to go down here. And grams I can turn into moles. Okay. Next step, last unit was to go from moles of one stuff to moles of another. We're ready to change what we're talking about. And that's where we're at here too. We're ready to change what we're talking about. I can change from moles of CH4 to kilojoules.
You can change to kilojoules, or do we have to change
Nope.
kilojoules?
Nope. Because my equation says that 1 mole makes 802.2 kilojoules. That 1 mole of CH4 makes 802.2 kilojoules.
What if it would be 2 CH4?
Then I would have been 2 moles make 802.2. So I copy these numbers out of the equation just like I did for mole to mole.
Okay, so basically we would have 2 CH4, we just put under the 802.2 kilojoules
Yep.
of 2.
That's right. Yep. And we'll do one like that in just a second. This works out to be 515 kilojoules. 10.3 divided by 16.05 times 802.2. Now, it's not always 802.2. That's just for this reaction. Different reactions give off different amounts of heat. So same equation. How many liters of O2 would be required to produce 23 kilojoules of heat? So I'm going to start off with the 23 kilojoules. What unit do I want to get rid of? Kilojoules. Because it says kilojoules here, kilojoules has to go on the bottom there. What can I turn kilojoules into? Because I have this equation, I can go to moles of anything in that equation. And since they asked me about O2, I'm going to turn it into moles of O2. And the moles of O2 has a 2 in front of it. So 2 moles of O2 will make 802.2 kilojoules. So if I can get kilojoules out of the equation, I get moles out of the equation. And then I get rid of moles of O2, and they want liters. And 1 mole is 22.4 liters. Hugely different than what we were doing before? No, we're just reading another number out of an equation because they put another number in the equation. So you push those buttons. 23 times 2 divided by 802.2 times 22.4 equals 1.3 liters of O2. So we can read the equation in kilojoules and moles, just like we could read it in moles and moles. And that's where we're going to get our conversion factor. So instead of changing chemicals, you change to energy. And it takes one less conversion factor, because you're never going to turn kilojoules into grams or liters. Does that make sense? Okay. So I get to practice some of those tonight. Have a good one.